In this video, we're going to go over the periodic properties of elements and how they vary across the periodic table. I will note that compared to other sections even, this will be very term heavy. There's very few problems to solve. It's just going to be, here are a bunch of rules to learn. But there will be some summaries we could use at the end that can help out with that to help keep them all straight. So many properties of elements vary based on their place on the periodic table. These properties include size of atoms and ions, ionization energies, and electron affinities. We will cover all three of these starting with size. So in terms of size, we first have to define what the size of an atom is. So the covalent radius is defined as 1/2 the distance between the nuclei of two identical atoms when they are joined by a covalent bond. Note that depending on the rest of the stuff around an atom, it will change slightly what the distance between these two atoms are. So when calculating covalent radiuses, like if you were to look one up, it will be the average of a very large number of molecules that we have detected before. So when I say covalent radius, it is half the distance between the nuclei of two identical atoms when joined by a covalent bond on average. So as you go down a group, so that means you're going down the periodic table, the quantum number n increases by 1. For this reason, the electrons are added to a space that is further away from the nucleus. Remember, we said as n goes up, it gets further and further away. This means that the size of the atom is going to increase as you go down a group. Because the electron gets further away, it is larger. So if you compare two atoms that are similar, but one is above the other on the periodic table, the one that is below is larger. For example, lithium and sodium occur on top of each other. Lithium above sodium. Sodium is larger because its last electron is in the 3s orbital, while lithium's is in the 2s orbital. To help with calculating as you go across the periodic table, it helps to use a concept called effective nuclear charge, or Z effective. This is the pull exerted on a specific electron by the nucleus, taking into account the fact that electron-electron repulsions occur. So for hydrogen, there's only one electron, so the nuclear charge and effective nuclear charge are equal. For all other atoms, the electrons of interest are partially shielded from the pull of the nucleus by the other electrons. In effect, the electrons get in the way of the outermost electron feeling the nucleus, because the nucleus is very positive, but it's already interacting with some closer electrons. So the outermost electron doesn't feel as strong of a pull. Note, we will give you some rules to work on calculating Z effective. These were somewhat simplified. If you stay with us in chemistry longer, there are some more technical rules that will account for how this shielding changes in different environments. We're going to simplify it here, though. So core electrons in particular are really good at shielding, and this probably isn't surprising. The idea is the ones that are closer to the nucleus block the ones that are further away. So each time we move from one element to the next across the periodic table, Z increases by 1. But the shielding increases only slightly to those electrons being added to the valence shell, causing the atom to decrease in size. You're still in the same energy level N, so as you go left to right across the periodic table, it gets smaller. Now to calculate Z effective, a simplified form of this equation is you can use that Z is the nuclear charge, and you can subtract from it S, the number of core electrons. Technically, some of the non-core electrons shield a little bit as well. We won't worry about partial shielding, but each of the ones in the middle shields completely. And so this will let us compare Z effective of two atoms. It helps explain why an atom to the right is smaller, even though it has more electrons, which might at first sound like it should be bigger. So here's an example from your text. The radius, is as we said, was identified as the distance between the nuclei, half the distance between two nuclei when the same atom is bonded together. And as we can see here, for example, francium here in the bottom left is the largest atom we have here. Whereas, okay, helium's actually the smallest. I'm going to worry about things. I'm not going to touch the noble gases as much. Their properties are a little different, but it works fine for size. But if we think of the things we tend to react a lot, fluorine is fairly small because it's towards the upper right. So what this means, if you think about the periodic table like this, as you go this way, down and left, you get large. Up and right, you get small. And since noble gas is the furthest to the right in their period, the left to right area, they'll be the smallest as well. So this gives us a general trend for atoms about whether they are large or small. This is another example of just what that looks like in terms of measurements of each of these atoms. The y-axis is the radius in picometers. The x-axis is atomic numbers. And you'll notice those dots in blue are the noble gases. So they tend to be the smallest of the atoms around them. And then once you gain another electron past noble gas configuration, you have a new n level. So these are our largest atoms, where they've gained a single electron, which lets them be very large. Then as you go left to right across the periodic table, those atoms are gaining electrons, but they're not going to a higher n level. So the nucleus is also getting stronger. There are now more protons, so it's being pulled on more and more strongly. Note that when you get to the transition elements, this pattern isn't perfect. You'll see there's sometimes where it goes down and up. Those energy levels can have a bigger effect, but the trend is mostly still true. It is generally getting smaller as you go right, and it is getting smaller as you get smaller, like you go, not smaller, as you go further up. So up and right, that's the value where you're going to get small atoms. Down and left, that's where you're going to get large. So just a reminder again. Large, small. And I think for all these properties, if you think of this line going across, you can figure out where things are likely to be, and that can help with remembering it. In a sense, you can use the periodic table to compare two atoms and say which should be larger or smaller. So we can also have what's called an ionic radius. This is the size used to describe an ion. So a cation always has fewer electrons and the same number of protons as a parent ion. So if you were to compare sodium to sodium plus has fewer electrons. As electrons are removed from the outer valence shell, the remaining electrons experience a greater effective nuclear charge and drawn even closer to the nucleus. Therefore, a cation is always smaller than the atom from which it is derived. And I love saying that word always when we get to, because a cation is always smaller. So sodium versus sodium plus, this is larger, this is smaller. And you could do that with any cation. Similarly, but in the opposite direction, an anion has more electrons and the same number of protons. Therefore, it has a greater repulsion from the electrons and a decrease in Z effective. This causes valence electrons to get further away from the nucleus. Therefore, an anion is always larger than the atom from which it's derived. So Cl versus Cl minus. Cl minus is larger. Cl is smaller. Now, we also know that the radius of the cation is smaller than the parent atom. These are two examples. So aluminum gets smaller when it loses 3 electrons. It goes from 118 picometers to 68 picometers. The people in the textbook that wrote this did not put their units on these. I would count a point off if I was doing it on their exam. So make sure we get those. And sulfur gets larger. It gains 2 electrons. It goes from 104 to 170 picometers. So cations get smaller, anions get bigger. When you add more electrons, the atom grows in size. When you take electrons away, the atom shrinks in size. Now, sometimes we'll have atoms that have the same number of electrons but different numbers of protons. We call these isoelectronic. So isoelectronic means same number of electrons, since iso means same, electronic, electrons. So an example here would be if you were to compare the atoms N3 minus, O2 minus, F minus, neon, sodium plus, Mg2 plus, Al3 plus. These are all 1s2, 2s2, 2p6. And then there's a second example where everything is neon, 3s2, 3p6. For atoms or ions that are isoelectronics, the only difference is the number of protons. So that's the only thing that can affect the size. If you have more protons but the same number of electrons, it should shrink the atom. The protons are pulling the electrons in. If you have fewer protons, you'll get larger and be further away. So if you compare two atoms that are, or ions, sorry, that are isoelectronic, the one with more protons will be smaller. So for example, of these, let's say we were to compare O2 minus to Mg2 plus. So the first step is to make sure that you identify that these have the same number of electrons, and they do. They both have 10. Oxygen starts with 8. If it gains 2, it goes to 10. If magnesium starts at 12 and loses 2, it also goes to 10. So you have to check first, are they isoelectronic? If so, then which one has more protons? Magnesium has 12 protons. Oxygen has 8 protons. Therefore, magnesium will be smaller and oxygen will be bigger in the case of these two ions. So it is possible to compare two different ions as long as they are the same number of electrons. Now, that was all for the first trend. we have two more trends to cover. Our second trend is ionization energy. So first, what does this mean? The word ionization has to do with forming an ion from something that is neutral. So the first ionization of an atom, and we use X just to represent a generic atom, is how much energy is released when you lose an electron. Then you have the second ionization energy. That's how much when the ion that has one already lost an electron, when it loses a second one, how much energy is released when it does that. So every time we have this happen, it's going to cause, there's going to be an energy associated with it. And I just realized I misspoke. I said the word released, but I'm having to put energy in to get the electron away, right? The electron is attracted to the atom. So I misspoke. The way we should say it is how much energy it takes to do this. So that's what ionization energy represents. How much energy do you have to put in to be able to remove this electron? And note, it will always take some amount of energy to remove an electron, because otherwise it wouldn't have been there in the first place. It wouldn't be bound to the atom, so it wouldn't be connected. As long as it's connected in some way, it takes some energy. Now, some atoms take very little, some take a lot. And you can keep doing this by naming them. Ionization energy 3 is enough to lose 3, the third one, then the fourth, and the fifth, and so on. So what are the trends of the ionization energy? So first, like I said, energy is always required to remove electrons. So things that can help us, as size increases, ionization energy decreases because the electron is further away from the nucleus, it's less well held, it can escape more easily. So the general trend is that first ionization energies tend to decrease down a group and increase across a period. So what that means is, let's see, so if we're decreasing down a group and increasing across a period, that means low groups and high periods will have the highest. Hey, it'll go like this. So if we go back to here, we have high ionization energies. I'm going to substitute that for IE there. And then the bottom left, we have low ionization energies. So atoms that are small tend to also have high ionization energies. Atoms that are big tend to have low ionization energies. Note there are some deviations from these trends, like if you compare two atoms next to each other at times, but we're going to focus on this trend primarily for the course as the general trend, not so much trying to get the individual exceptions out of it. So here's an example of a graph of this information with the y-axis being energy and the x being atomic number. You can see that it starts low at the beginning of each period and then gets higher and higher until you get to the noble gas form, where the noble gas really doesn't want to lose an electron. It's got a stable configuration. It takes more energy to remove a noble gas electron than it does the other atoms before it. And so you can also see there's some up and downs in some areas, but the general trend is that you start low and go up as you go across the period, and each time you get to a new one, you jump back down. So here is a version that has numbers attached to it. You don't have to know these numbers, it's just to give you a feel for it, so you can take a look at it, and you can see that, yes, fluorine is one of our highest. Francium doesn't have one listed because it really doesn't like to have electrons. It's hard to get it stably without one, but you can see that cesium is very low compared to the other numbers around it. Rubidium as well, the things on the far left, really don't like their electrons. So the idea behind this is that it is true that, for example, cesium is highly reactive and will basically always get rid of its electrons if it is in contact with some other atom. So as you might imagine, if cesium and fluorine were close to each other, fluorine desperately wants to keep its electrons in comparison. So it's easy for cesium to give its electrons up and for fluorine to pick them up. We will talk about this in the next chapter where we talk about a concept called electronegativity. But the part we can see here is some atoms hold on to electrons more strongly than others. This means it is possible to form ions even though all atoms somewhat like their electrons, because other atoms can have more energy from gaining electrons compared to other atoms losing them. So even though it always requires energy to lose an electron, there are plenty of chemical reactions where that happens naturally because one atom losing takes some energy, but another atom gaining releases more energy. So as long as there's a difference in that way, you can still have chemical reactions and atoms can still lose electrons. So how do we deal with successive ionization energy? So like IE 2, 3, 4. So removing an electron from a cation is more difficult than removing it from a neutral atom because you've got a greater electrostatic attraction to the cation. You've already removed an electron. So now it's got a stronger positive charge on all the remaining electrons. So what this means is every single time you go up an ionization, so IE1 to 2 to 3 to 4, each one you go up, it gets harder and harder. And there is always an increase. Now, the increase isn't always the same. Sometimes it's a small increase, sometimes it's a gigantic increase. But there's always an increase. It is always harder to remove a future electron compared to an earlier one. So removing electron 2 is always easier than removing electron 3, which is easier than removing electron 4. So those ionization energies have to keep increasing. Now, what you may notice here is, if you look carefully, there's actually a pattern. So we have a bunch of different elements and their ionization energies. Now, what you'll note, let's take potassium, for example. Do you see how between IE1 and IE2, there is a jump of 2,600? But if you go to calcium, there's only a jump of about 500 between them. It's less than 1,089, it's like 550. So the jump from 1 to 2 for potassium is much larger than the jump from 1 to 2 for calcium. But if you go from 2 to 3 in calcium, now there's a jump of 3,800. It's very large. Now scandium does something like calcium at first. Oh, it only goes up by about 600. Then it goes up by 1,100. And then it goes up by 4,700. And what you'll see is there's this barrier that gets passed where the number suddenly gets much larger. And so, oh gosh, and so there's a weird one there. That one doesn't match where I expect it to be, but that's okay. Did I do this right? Yeah, that jump. This jump is actually larger. That was not what I predicted. It doesn't match. Let me make sure I've got the right thing on my periodic table. GA. Oh, right, because you've got the d electrons there too. Okay, the important part here is where we see our largest jumps. We're going to not worry about gallium right here. Just don't worry about it for this discussion. There's some other things about it when it's removing electrons from the d orbital. But for our first three, we can see a pattern very well that when you remove the valence electrons, it's easier than removing core electrons. And so that happens here. Now, this particular set of examples deals with d orbitals. If you were to take something from one of the second or third period, this pattern would continue much more obviously. And I realize that, and I will change that in the future, because when you take it from the s and p orbitals only, it's once you get past all the valence that the core suddenly is way harder to take away from. So that's a pattern we will see in the ionization energies. Removing valence electrons is easier than removing core electrons. And so while the number always goes up, it goes up more when you make the transition from valence to core. So potassium has 1 valence electrons. That's why IE2 is so high. Calcium has 2 valence electrons. That's why IE3 is so high. Scandium has 3 valence electrons. That's why IE4 is so high. And then with gallium, you've got things in the d orbital. Gallium's actually way further over because that's after about, you've got 10 transit. You got 3d10 in there as well. Or is that 3? Yeah, it's 3d10. So that one's more complicated with that. Because if you kept going across and gallium's not going to naturally lose enough electrons to get all the way to its noble gas configuration, because gallium would have to lose, let's see, 13 electrons to do that. And that would be so hard to do. You're not going to see gallium 13 plus. So it's got some different properties. We'll deal with it otherwise. But these are still true measurements. But for the first three, you can see the pattern really well. Now, so at some point, like I was saying, there's always this large increase. And the larger increase tends to occur when you start removing core electrons instead of valence. And the example here was about scandium and gallium both having 3 valence electrons. But that's why you see the large increase after 3, because that's where you're out of the 4s orbital and the s and the p, and you've removed those. And so once you get to those, then you start getting into things that are further down. So gallium also has the same number of valence because they both have 3. Should I have written 2? Scandium, oh no, scandium and gallium do both have 3. Okay. Now finally, sorry for that short aside, just checking something. We have electron affinity. This is the energy that is gained by gaining an electron. So when an element gains energy, when an element gains an electron and energy is released, we say that it accepts the electrons, that has a negative electron affinity. Technically, some atoms really don't want electrons, and you might have to put energy into it. Depending on the textbook you use, some will just list these as 0, and I think that's what happens in the most common periodic tables that you look up like on Google. But it can be because it actually takes positive energy. It really doesn't want that electron. It's actually making the molecule, the ion, unstable. So, in general, it becomes easier to add an electron as the effective nuclear charge of the atom increases. Therefore, electron affinities become more negative across a period. So that means you go left to right. As you go towards the right, it becomes more negative. which is going to be a larger electron affinity. It's how much energy is released. And by larger with the terms electron affinity, I mean the absolute value. So if I ask a question about electron affinity, I'll be very careful how I word it in the sense of when does it release more energy? Because the word release implies negative there. I will note that among these three trend types, electron affinity tends to have more deviations from this trend than the other two. And you'll notice we just talk about it going across a period. It's not as clear a trend going up and down across a group. So it's just really across left to right. And I use this trend less because it has more exceptions to it, I find. So for example, you can see here are some examples where you have, if you compare, like fluorine is much larger than oxygen, which is larger than nitrogen at 0 versus carbon at 123. But you'll notice there are more exceptions if you actually go through here. So I tend to find it a less useful trend compared to the others, but it's still one we teach, so I'll be consistent with everybody else and talk about it. But it's one where I'm much more likely to look at experimental data for it, unless the atoms are really far apart. If you're really far apart on the periodic table, it is unlikely that you have a exception to your rule that you're working with. So let's do some practice. What I suggest here is you pause the video and try all of this, and then I'll go over all of it. Okay, hopefully you paused it and you gave it a shot. So for the first one, which atom is larger, we have to look at their position on the periodic table. So fluorine is to the right of nitrogen. Therefore, nitrogen will be larger because they're in the same group. They're in the same period, but one is further over. So the one that is further to the right is smaller, the one that further to the left is larger. Then you have K and Na, potassium and sodium. Potassium is in a larger group number, further down the periodic table. It's in period 4, whereas sodium is in period 3. So if you're in period 4, you've got a 4s electron. That will make you larger than sodium that only has a 3s electron. Finally, you have phosphorus and germanium. So phosphorus is both to the right and further up. Therefore, phosphorus will be smaller, whereas germanium will be larger. Remember, the trend is, if you got a periodic table, you've got large over here and small over here. Now we have some ions. We need to pick the largest pair. We said that cations were always smaller, so magnesium is larger. We said anions were always bigger compared to the atom, so chlorine minus is bigger. Now with chlorine minus and F minus, they're both the same ion, so the trend will match what their atoms would be because they're both -1. And so chlorine is larger than fluorine, so chlorine minus is larger than fluorine minus. So chlorine minus is bigger. And then similarly, if I compare lithium plus and sodium plus, sodium would be larger than lithium, so sodium plus would be larger than lithium as well. So for the trend of ionization energy, we have the question which of these has a larger ionization energy. So we compare sodium and magnesium. Sodium will require less energy to lose its electron because it's further to the left. And so magnesium will require more energy. If we compare chlorine and bromine, chlorine is on top of bromine, so the atom that is further up is going to have a higher ionization energy. It's harder to remove its electrons compared to bromine. Bromine's electrons are further away. Similarly, if I compare sulfur and fluorine, fluorine's electrons are closer to the atom and they're held more tightly, so sulfur is going to be the one that is harder to remove. And then finally, where do we expect the largest ionization energy increase to happen for aluminum? Aluminum has 3 valence electrons. It is neon, 3s2, 3p1. So the first 3 electrons will be easier to remove than the fourth one by a large amount. So we expect a very large increase when we get to ionization energy 4. So it'd be something like 600, 1200, 1800, 9600, and then IE5 is still bigger, but it's like 10,200. So it's not that it won't keep on increasing, but it's about the amount of increase. We expect a much larger increase for ionization 4 for aluminum. So that is the end of my section on periodic trends. Hopefully that helps out. The biggest thing with these is being able to keep track of them. So I will real quick summarize that. So we said large and small. We can also say this is high ionization energy, and this is low ionization energy in the bottom left. And then in the top right, we also have high electron affinity, and that's mostly about the fact that it is to the right. And then we have low electron affinity towards the left. And so notice the trends with electron affinity tend to match up with ionization energy. The exceptions might be a bit different. And specifically the word high and low, I mean in terms of absolute value. High electron affinity means that I see a high amount of energy is released when it gains an electron. So it's important to be careful with how you word electron affinity, because you might think of it, well, it's a large negative number, which is a small number. So I'm specifically talking about how much energy is released when it gains an electron. Is high amount is released for the things on the right, a low amount is released for the things on the left. So if you can get those three trends down, and make sure you can also do it for ions, you can do all the stuff within the periodic trend stuff by looking at a periodic table, and that's all you'll need to be able to get all these right. So hopefully it helps out, and I will see you later.